Everybody have a look up at the board now. Worksheet number 16, questions 1 to 4 were your homework last night. I'd like you to take a look at questions 1 and 2 and see if there's either of those that we need to go over. Then we'll take a look at 3 and 4 for the same thing. Questions 1 and 2. Any issues with either of those questions, 1 or 2? Can we do 2? Absolutely, yeah. 1's good. Okay. Number 2 says a 7 centimeter tall object is placed 4 centimeters in front of a diverging mirror. We're not too concerned about the whole centimeters thing here. Normally we circle that and draw attention to it because it's non-standard units. It's still non-standard units, but we can go with centimeters as long as we're consistent through the whole question. So we're not going to worry about circling that so much, but we are going to circle diverging mirror. That's really important. Okay, that tells us that we have a negative focal point, a negative focal length. Hey, that's a really, really easy place to make a mistake. Tell you, if we had a question on a test right now with a diverging mirror, I would bet that at least 40% of you would get that wrong because you'd make the focal length positive. Hey, that's a big number. That's a significant number. So let's draw attention to it to reduce that number. Okay, let's all of us draw attention to it so that we all end up getting it right. Focal length is 8 centimeters, really negative, right? We want to find the image distance, the image height, and the magnification, and we want to find the characteristics of this image. So there's quite a bit we got to do here. We have a value of HO here. We're going to make that positive. We're not told that it's right side up, but we can assume that it's right side up. It's 4 centimeters in front of a diverging mirror. That's going to be DO, and DO is always positive for us in Physics 30. Focal length 8 centimeters. Again, I'm going to put a little negative there as well, just to remind me again. Listen, even if you get it right without reminding yourself, what's the harm? What's the harm in drawing attention to it in a couple places? Okay. Worst case scenario, you just wasted a little bit of ink by writing down F was equal to a negative value a couple times. Okay. Best case scenario is it helps you not to make that mistake when you go to plug it into the equation. We want to find the image distance, DI. We want to find the image height, HI, the magnification, and then we want to find the attributes based on some of the numbers that we get there. Or if you want to draw a ray diagram, you could do that to find the attributes as well. All right, we got 2 equations. We're not sure which one we're going to use first, especially when we got a problem where we're solving for 3 variables and we only have, what, 3 variables. Solving for 3 variables, we only have 3 variables. We're not sure which one we're going to start with. Start with one of them. You see what happens. I'm going to go with the 1 over F is equal to 1 over DO plus 1 over DI, even though I don't know that that's the best one to start with. I might not be able to solve for anything with that. Whatever. Okay, if I can't, then I'll go to the other one. I know what F is. It's 8.0 centimeters. So we're going to say 1 over 8 is equal to 1 over DO, which is 4, yeah, plus 1 over DI. Is that right? No, it's not. What's wrong, Stephanie? It should be negative 8. We're not going to forget that because we've drawn attention to it in 2 different places. Honestly, as I was just going through that, I would have absolutely forgot to put a negative there in that equation had I not drawn attention to it up above. Okay, I'm one of those people that would make that silly mistake, not all the time, but a lot of the time, if I don't draw attention to it, so, like I did up there. All right, we open up our calculator here. We use the same little trick that I taught you yesterday with the calculators. We're going to say negative 8, x to the minus 1. That's the same as saying 1 over neg 8. We're going to bring the 1 over 4 over by subtracting, so that becomes 4x to the minus 1 equals negative 0.375. Is that my answer? No, but we're close, right? What are we going to do with that? Carolyn, what are we going to do with that? Yeah, flip it over. So we can go 1 over that, or we can just go that to the minus 1, x to the minus 1. We get negative 2.6667. And that's going to be in centimeters. Let's round that to negative 2.67 centimeters. I wrote down the unrounded number in case I need to use that later on, but my final answer for DI would be negative 2.67. All right. So we got DI. Let's try something else now. Let's go with our magnification equation. Negative DI over DO. Negative 2.66667 over DO, which is 4.00 centimeters. What does that give me? Negative, I don't know, is that 0.667? Is it negative 0.667, is that right? I think Kaylee's begs to differ with you. What is it, Kaylee? Right. 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 Negative DI. Okay, just because DI is a negative value doesn't mean we can just automatically drop a negative. Negative DI, negative 2.6667, which gives me a positive value for the magnification. So positive 0.6667, or rounded to 3 digits, 0.667. No units with that. If you want to put an X beside it, 0.667 times the size, that's okay. It doesn't really matter. All right, good. We got magnification. Now let's finally do the image height. Let's say M is equal to HI over HO. No negative in front of that one, right? HI over HO. We're going to say HI is equal to M times HO. 0.666. Let's use the unrounded number. 4 or 5 decimal places. Multiply that by HO, which is 7. What does that give me there? 4.67? And that's a positive value, right? All right, so now we got HI. Now we just need the attributes or the characteristics of this. Larger, smaller, same size, right side up, upside down, real or virtual. Give me one of them. If you can find one, give me one of them. Yep. How do you know it's smaller? Good. If the magnification is between 0 and 1, it's a smaller image. Okay, there's the first characteristic. Good. Give me another one. How do you know it's virtual? Okay. Yeah, that's not the way that I was thinking of it, but that's good logic still. Adam said that it's virtual. We know that because it's a diverging mirror. A diverging mirror, if you think back to your array diagrams, always produces a virtual image. We knew when we started the question, if we looked at array diagrams, that it was going to be a virtual image, right? How else can you determine this is virtual? Besides that, I'm not gonna suggest that you don't use that logic because that's good. The only problem is if it's converging, you don't know, right? All bets are off. So you have to go to the other method for that. Chase? What variable you're looking at, though? Right. If DI is negative, it's going to be a virtual image. Okay, so both sets of logic are good then. Finally, what do we got here? Right side up or upside down? It's upright. Matt, how do you know? That was you that said that, right? Well, okay. Keaton just said it's always upright if it's a diverging mirror. If we look back to array diagrams, it is. Okay, if we forget those array diagrams, we have to go with the math and the sign conventions. How do we know that it's upright? Because the image height is a positive value. Yeah, HI is positive. Good. We good there? All right, let's take a look at 3 and 4 here. Take a look at the answers at least and see if there's any issues with those questions. See if we need to go over either of them. Any issues with 3 or 4? They're both good? No issues? Okay. All right, here's what I'd like you to do with this stuff for homework, please. I would like you to finish off the worksheet except for number 6. Okay, I would like you to do for homework, please, question number 5 and 7. Don't do question number 6 because there's an issue with the wording in question number 6 and it's just not written all that well. So we're not even going to bother going through that process. Just do 5 and 7. In addition, we've got a few check and reflect questions on page 665. I'd like you to do question 4 and 5, question 7 and 8, and question 11. So 5 check and reflect questions, 2 worksheet questions, 7 questions total. Today we're going to talk about refraction. The very first day of this unit, we talked about electromagnetic radiation. We talked about 4 properties of waves that are exhibited by electromagnetic radiation, lending support to the wave theory of light. They were polarization, diffraction, interference, and refraction. Refraction we defined as the bending of light. You guys have all seen this before, one place or another, whether it be the pencil in the water or whether it be the golf ball retriever in the pond as you're trying to get the golf ball out or whatever. Okay, you stick something in the water. If it's at the right angle, it appears to be bent. It appears to be bent because the light that's coming off of that object, the light that reflects off of that object, when it goes from the water to the air, changes direction. The light bends. That's called refraction. Our eyes are therefore tricked into thinking the object is someplace other than where it really is. We know in this diagram here, this pencil continues on in a straight line. Under the water, it really goes this way, but it looks like it goes in another direction because the light bends, and it's the light that we see, not the pencil itself that we see. Refraction is the bending of light, and it's due to the light changing speed when it goes from one medium to another, either slowing down or speeding up. I'll show you exactly what I mean by that in 1 second here. Caden, question?
So I just noticed sometimes, like, for example, if you have a glass like this,
Yep.
you look at the side, sometimes it looks like it's not bent.
Yes, it does. Now, Caden's question, if you didn't hear it, good question. Sometimes if you have the pencil in the glass and you look at it from above, it looks to be bent. If you look at it from the side, well, at certain angles from the side, it doesn't appear to be bent anymore. It all depends upon the angle that you're looking at it from. Okay? In the end, it's a matter of, literally, it's a matter of perspective. Okay? If you're looking at it from a certain angle, then it's not going to appear to be bent. Basically straight on, then it doesn't appear to be bent. If you look at it from some other angle, then it does appear to be bent because of the angle at which the ray strikes the boundary, strikes the new medium relative to you. Okay, so yeah, that's not a surprise. Sometimes it's going to appear to be bent a lot. Sometimes it's not going to appear to be bent very much or even at all, depending upon what angle you're viewing it at. Years ago, it would have been 2006, I think. I went to Disneyland with my family, and we're staying at a hotel across the street from Disneyland. My room overlooked the pool, okay, and it was 6:30 in the morning, 7 o'clock in the morning, I'm not sure, somewhere around that. Looking out the window, getting up, getting ready to go to Disneyland, looking out the window, and there's a guy cleaning the pool. And he's got one of those big, long filters, you know, big, long sticks with a filter on the end of it that he's trying to sweep the leaves and the dirt out of the pool with. And it's really, really long. Right away, I ran and got the camera and snapped a picture of it. And my wife said, "What are you taking a picture of?" I said, "Of the pool guy." She thought that was a little bit odd, but I said, "Well, no, there's refraction. Like, there's lots of refraction here." In the end, the angle that I was watching that from, it was a perfect example of it. Okay, here's the pool. Okay, this stick that the guy was holding was bent like crazy. Like, it was a perfect example. Now, I have no idea where that picture ever went. Okay, otherwise, I'd put it on the slideshow because it was perfect to illustrate this. Had I been looking at it from his angle, you know, I wouldn't have seen at least as much bending there, maybe nothing at all there. Okay, so it does depend upon what angle you're looking at it from. The bending of light due to the light going from one medium to another and changing speeds. I want to show you a diagram that isn't really light, but will illustrate what happens when light does go from one medium to another. In other words, the change in speed. The bottom side of this line is going to be pavement, asphalt. It's a paved parking lot. The top side of this line is going to be a swamp. For whatever reason, still haven't figured out a good reason why we've got soldiers in this parking lot marching, but they are. I still haven't figured out why you're above all of this in a helicopter watching. So you're above it. As you look down on these soldiers close together, they look like a line. It looks like a wavefront, like a crest of a wave. 2 seconds after you've first seen them, you see them again. Soldier number 1 is up here because he's marching, right? Soldier number 2 is up here. Soldier number 3, number 4, Number 5. Number 6, where's soldier number 6? Well, he's in the swamp. He's marching forward, but he's in the swamp. So what happens to him as he goes into the swamp? He slows down a little bit, right? When he goes from one medium to another, he slows down. There's the wave now. 2 seconds later. 1, 2, 3, 4. Soldier number 5 just went into the swamp a little bit. Soldier number 6, he's take time in the swamp now. The wave front looks like this. 2 seconds later, oh, look at that. Soldier number 4 is just gone into the swamp. Soldier number 5 is completely in the swamp. Soldier number 6, well, he's still in the swamp. Poor soldier number 6. He's like, next time, I'm at the other end. Okay? I don't want to walk through that swamp. You see what happens here? The wave front was moving this way. The wave front is now moving this way. What does that due to? The wave has changed direction simply due to the fact that the soldiers that make up this wave have slowed down. Now, what else has changed? The speed has changed. The material has changed, right? The material that we're in has changed. We go from pavement to swamp. The material has changed. What else has changed? The speed. What else has changed? The direction has changed. The angle has changed. What else has changed? The distance between the crests, which we define as the wavelength. So when we have refraction taking place, the bending of a wave, or the bending of light in this case, okay, it happens because we go from one medium to the other and the speed changes. That results in the wavelength also changing, and it results in the direction also changing. We're going to define a term here called the index of refraction. The index of refraction is technically defined as the ratio of the speed of light in a vacuum to the speed of light in another medium. Whatever medium it is that you're trying to find the speed of light, the index of refraction for. So each material has its own index of refraction. Material A's index of refraction would be the speed of light in a vacuum as compared to the speed of light in material A. Material D would have an index of refraction that's equal to the ratio of the speed of light in a vacuum to the speed of light in material D. What does it really mean? I mean, that's our definition. But what does it really mean? How much light bends? The higher the index of refraction, the more light bends. The lower the index of refraction, the less light bends. Index of refraction is given by the symbol n, lowercase n. It's not the number of moles or whatever that stands for in chemistry. The index of refraction. How much light bends? The ratio of the speed of light in a vacuum, c, which, by the way, will always be 3.00 times 10 to the 8. Bless you. Divided by the speed of light in whatever medium that is, we're going to call that v. So if the speed of light in water, let's say, speed of light of water is, let's say, something like 2.2 times 10 to the 8 meters per second. If we divide 3 times 10 to the 8 divided by 2.2 times 10 to the 8 meters per second, we're going to get an index of refraction that's greater than 1 point something. The speed of light in glass is about 2 times 10 to the 8 meters per second. 3 divided by 2 times 10 to the 8 would be about 1.5. So the index of refraction in water would be about, I don't know, 1.4. In glass would be somewhere in the range of 1.5. Which one causes light to bend more? Water, that has an index of refraction of 1.4, let's say, or glass that has an index of refraction of 1.5. Glass has a higher index of refraction. It has a bigger ratio of speeds, and it has, so it has a bigger index of refraction, which of course is going to cause light to bend more. Hey, what are the units that we'd have for n? The index of refraction. Sorry? It's unitless. There are no units, right? Because it's a ratio. The units cancel out. We got meters per second over meters per second, gives me no units. The good news is it's a simple equation. The bad news is it's a lot like a chemistry equation, but variables in different places. And it's not on your data sheet. But it comes back to the definition, right? We got to remember what the definition for the index of refraction is. It's a ratio of the speed of light in a vacuum to the speed of light in the medium. If we remember that definition, this is an easy equation. Okay, it's a ratio, so it's C over V. Ratio is always divide, right? We learned that earlier this year. Always divide. C divided by V. All right? Now, what's this? Looks like a rainbow, doesn't it? It's exactly what it is. Yes, it is. Yeah, it is. Pink Floyd, huh? We're going to talk about something called dispersion here right now, which is real closely related to what we just talked about. Glass has a certain index of refraction, about 1.5. Although it does vary a little bit depending upon the type of glass you have. Okay, every different type of glass has a slightly different index of refraction. But let's say it's about 1.5. When we give you the number for the index of refraction of a particular type of glass, what we're really giving you is usually an average. Because the reality is the index of refraction, even for a particular type of glass, is actually a little bit different depending upon the type of light that we're using. In other words, red light, that produces a certain index of refraction in glass. Violet light will produce an index of refraction that's almost the same, but slightly different than it is for red light. What effect does that have? Well, if the index of refraction determines how much light will bend because of how much it changes the speed, then that's going to cause each color to bend a slightly different amount. That means if we have just red light going through this prism, going to go through like this, no problem. But if we have white light, which is what we normally see, okay, around us all the time, coming from the sun, coming from the light bulbs, consisting of all different colors, then what we see is this dispersive effect where the light splits up. Red light produces a certain index of refraction. It bends a certain amount. Violet light has a different index of refraction. It bends a different amount. Violet light bends more than red light, so when it comes out the other side, they're separate. They went in together, they come out separate because each one bent a different amount. When you look at this diagram here, can you tell me which color produces the highest index of refraction for glass? In other words, glass is the highest index of refraction for violet, because violet bends the most. It has the lowest index of refraction for red. Low frequencies, low index of refraction. High frequencies, high index of refraction. Now, the difference between the index of refraction for red and for violet is not very much. It's not great at all. We say the index of refraction is about 1.5. It might be a little less than that for red, a little bit more than that for violet, but we're not talking about, 1.3 and 1.9. Okay, we might be talking about, 1.49 kind of thing. They're still all very close, just not exactly the same. And you try to do this with a little prism. It's actually hard to make it work. It's hard to make it work because you got to get the prism at just the right angle, and it's hard to do. The best examples of this that I've ever seen have been purely by accident. Once I remember I was at a friend's house after school in my friend's living room where there is a couch right here and there's a fish tank right here. The sun is over here. The sun comes in the front window, goes through the corner of the fish tank right here, which makes a perfect prism. If it goes through at the right angle, it splits up the white light from the sun, forms a perfect rainbow on the wall. So I'm sitting there after school and I notice this perfect rainbow on the wall formed by dispersion of the light going through the fish tank. Again, purely by accident. Didn't last very long. How come? Disappeared pretty quickly. Why? because the sun moved. It's in a different spot real quickly, right? The other place that I've seen a real good example of this is in this school. And I've seen it since we moved into this building about 8 years ago. I've seen it maybe a dozen times, maybe not even that. If you walk to the atrium and then walk past the cafeteria, so here's the cafeteria, here's the display cases in the atrium, right, in the corners there. Okay, here's the atrium itself. The light comes in these high windows right here. Now, one day I remember years ago, I noticed as I was walking right after school past the cafeteria, on the floor right here, a perfect spectrum, a beautiful spectrum. What was it caused by? The light coming through these windows up high in the atrium, going through the corner of this triangular display case, producing dispersion. Now, you got to be walking past at just the right time of day. How come? Same reason. Sun moves. Doesn't happen. Well, that's right. The Earth. The Earth does. Sun moves relative to the Earth. We also got to get it at the right time of year. Right? The sun's in a different position. You're not going to see it every day after school at the same time. You're going to see it during certain times of the year for about a minute or two at a time. That's why I've seen it maybe 10 or 12 times over the 8 years that we've been here. I don't remember, Tristan. I don't remember. Yeah, I don't remember. I don't even want to. Here's what I want you to do, though, Tristan. I want you, as soon as the school day's over today, I want you to go sit outside the cafeteria for 15 minutes. That's it. Go home after 15 minutes. Because if it doesn't happen by 3:45, it's not going to happen. If it doesn't happen, then I want you to do the same thing tomorrow. And then the next day, and then the next day, until it happens. No, it won't happen at 20 after 3. It's sometime after school, but it's just within 10 minutes of after school. So sit there every day after school, Tristan, until you see it. And when you do, take a picture of it, okay? Does this make sense? What do you see on the screen over there, the pattern that's formed? It's a rainbow, right? That's how rainbows are formed. That's how rainbows are formed. When light comes in, white light comes in from the sun, it hits moisture in the air, which effectively acts as a lens or a prism. It splits up the light. It disperses the light. And we end up getting rainbows. Yeah?
Why does it take like
That's a good question. I don't know. It's funny because I remember very clearly, there's not a lot I remember from high school because it was generations ago. But I remember very clearly asking my physics teacher in high school the exact same question and getting the exact same answer as I gave you just now. I don't know.
I'm sure Google would know.
Yeah, you know what? I've actually looked it up, but I've never really found a good, real understandable reason why that's the case. I've looked it up probably 3 or 4 times over the years and just never found a good one.
They usually have double rainbows.
Here's an equation. Sine theta 1 over sine theta 2, V1 over V2, lambda 1 over lambda 2. Oh, what's this? N2 over N1. Be careful with that. 1 over 2, 1 over 2, 1 over 2, and then all of a sudden we got 2 over 1. What do these variables mean, and what does this equation mean? We said just a few minutes ago when we gave you that analogy with the soldiers marching in the parking lot, that when the soldiers, the wave went from one medium to the other, okay, one medium to the other, right? Index of refraction, one index of refraction to another index of refraction. Something changed. What changed? What was the main thing that changed? The soldiers did what when they went into the swamp? They slowed down. So the speed changed. There's a relationship between the medium and the speed of the soldiers, or the medium and the light speed. The speed changing caused what? It caused what? It caused the direction to change, the angle to change. The speed change also caused what? Let's go back to that diagram again. The speed changed, the direction changed. What also changed? The distance between the waves here. The wavelength decreased. So the wavelength changed as well. When we go from a low index of refraction to a high index of refraction, pavement to swamp, okay, you go from low to high, speed decreases. Wavelength decreases. And the angle decreases. So as you go from low to high N, everything else goes high to low. That's why we see sine theta 1 over sine theta 2, V1 over V2, lambda 1 over lambda 2, N2 over N1. Because as N goes up, everything else goes down. Now, the good news is this one is on your data sheet. And even though there's 4 parts to this equation, you only ever need to use 2 of them at once. So V1 over V2 equals N2 over N1. Sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. Whatever 2 parts happen to fit the givens you have the best. All right? Let's just real quickly identify a couple things with this equation, and then we'll do an example here. This is going to be theta 1, the angle of incidence. What does that mean? Well, the angle at which the light strikes the boundary as measured from the normal line. So if it's going like this, this would be theta 1. Theta 2 would be the angle of refraction. So it goes into a new medium. Theta 2 in this case is bigger than theta 1. It bends so that theta 2 becomes bigger. Theta 2 is that angle of refraction. What units do you think we'd use, by the way, for angle? That should be an easy one for us, right? No. No, it's degrees. Just kidding.
Can we use it? Can we do it?
No. It's always going to be degrees. Always going to be degrees. In Physics 30, you will never use radians for anything. In Physics 30, you'll use degrees for everything. Make sure your calculator's in degree mode and use degrees, please.
I'm going to currently have it in work now.
Now, I want you to take a quick look at this diagram for a second. In this particular case, the angle increased. If the angle increased, theta 1 is smaller than theta 2, then what do you think happened to the speed? Did the speed of light increase or decrease when it went from medium 1 to medium 2? What does it do? Decrease? No, it increased. If theta goes up, then V has to go up. Wavelength would also go up. What happened to N? It went down. It decreased. Right? Everything's related except directly related except for index of refraction. As V goes up, lambda goes up, theta goes up, N goes down. So in this case, theta increased, V increased, lambda increased, N decreased. Got it? Okay, V1 is the speed of light in medium 1. V2 is the speed of light in medium 2. Lambda, wavelength, okay? And of course, N, the index of refraction in medium 2 as compared to medium 1, right? Here's a little table that you don't have to memorize, obviously. You ever need any of these numbers, you'll be given the numbers on a test, probably not in the form of this table. It would probably be more like a page of information with a couple of these indices of refraction buried somewhere in that page of information that you'd have to pick out. But it's going to be there somewhere. You don't have to memorize any of them. The index of refraction of air, by the way, is on your data sheet. So that one might not be buried in a question. You have to look at your data sheet for that one. But on your data sheet, they actually listed as 1.00, not 1.0003. So that's the value that we're going to use, even when we're doing questions out of the textbook, 1.00, just to get us in that habit of using the number that's on our data sheet. What I also want you to notice here is that we're told that these are the refractive indices for sodium yellow light of wavelength 589 nanometers. Why do they specify that? Why don't they just say it's the refractive indices or the index of refraction? Tristan? Yeah, because the index of refraction for Violet light it will be a little bit different, not dramatically, but it'll be a little bit different. So this is specific to yellow light, but you know what? These numbers are close enough to use whenever. Okay, it's good enough. Unless you're given some kind of indication otherwise, then these numbers are good enough to use for whatever color of light we have, including white light. All right, make sense? Take a look at some of these indices of refraction. We can see that glass, a couple different values, depending upon what kind of glass we have. Air is a pretty low one, obviously, because if you look at the equation, N is equal to C over V, speed of light in a vacuum, 3 times 10 to the 8. In air, it's, well, rounded to 3 digits, it's still 3 times 10 to the 8. So it's going to be 1. Basically, it doesn't slow down, not very much, when it goes into air. What about water? Slows down quite a bit when it goes into water. Slows down even more when it goes into glass. Slows down the most when it goes into diamond. That's why diamond sparkles so much. Not that I'm aware of. I would never say never, but not that I'm aware of. The index of refraction of diamond is very, very high. Okay, much higher than it is for glass. Much higher than it is for glass. That causes a change in the speed of light dramatically for diamond as compared to glass. And ultimately, that's what causes a diamond to sparkle. Tomorrow or the next day, we'll go through that analysis of exactly why a diamond sparkles. Okay, you'll learn how to, well, if you're a guy, someday, buy a diamond ring that's good. And if you're a girl, learn how to know whether the man who's trying to propose to you is cheap or not, is trying to pass off cubic zirconium as a diamond, or even worse, glass as a diamond. All right, that's tomorrow though. Let's take a look at an example here, okay? Page 668, 13.3, it says yellow light travels from water into crown glass. From water into crown glass, medium 1 to medium 2. The light rays are incident on the crown glass at an angle of 35 degrees. That's going to be theta 1. They're incident on the crown glass. They're striking the crown glass. They're going from the water to the boundary between the water and the crown glass at 35 degrees. We want to find the angle of refraction. We want to find theta 2 here, the angle that it comes out of the crown glass water boundary at. Now, if we look back at the table, we know what the value of N1 is. Okay, from water to crown glass. N1 is going to be, if we look at this, 1.33. N2, the crown glass, I always forget which is which, crown glass or quartz glass. Crown glass is 1.52. Let's use this part of the equation and this part of the equation. Sine theta over sine theta equals n over n. Which n? N2 over n1. Let's plug some numbers in here. Sine 35 degrees over sine theta 2 equals n2, 1.52 over 1.33. By the way, if you mix up these two numbers here and go n1 over n2, and it's a multiple choice question, what do you think is going to happen? They'll have that answer. They're not trying to trick you. They're just trying to not tell you that you've made a mistake. They're not tricking you into putting a certain answer. They're just not going to tell you that you made a mistake. Any more than if it was a written response test, we wouldn't tell you that you made a mistake, right? All right, let's do some math here. Let's first of all go sine 35. Make sure you're in degree mode. Okay, click up here. Yeah, we're in degree mode. Sine 35 equals 0.5736. Now let's do 1.52 over 1.33. That gives us 1.1429. Now, how are you going to get theta 2 here? We've simplified it a little bit, but still got to do something important here to get theta 2. What are you going to do? Yeah. Yeah. Let's take it up one step at a time here. Let's say 0.5736 equals 1.1429 sine theta 2. Okay, let's take the 1.14 over by dividing. Good. 0.5736 divided by 1.14. 0.5019, let's second function sine or inverse sine of whatever we got there. You get 30 degrees. Not sure how many digits we were supposed to have there. Looks like 2 digits. Theta 2 is equal to 30 degrees. Let's draw this out for a second here, okay? We went from water to glass. The ray of light was going in at an angle of 35 degrees. The ray of light comes out at an angle of 30 degrees, a smaller angle. What do you know about, well, the angle has gotten smaller, right? What do you know about the index of refraction? If the angle has gotten smaller, the index of refraction has gotten bigger. What do you know about the speed? Speed's smaller. What do you know about the wavelength? The wavelength's gotten smaller as well. Is that okay? How many people here wear glasses? One? Contacts or glasses, right? If you wear contacts, you've probably got glasses. You wear the odd time. I would be willing to bet, quite a few of you actually, I'd be willing to bet that all of you that have glasses are nearsighted. That means you can see near things. So if you take a piece of paper, I'm nearsighted. Okay? Most people that are, young or middle-aged, if they need glasses, they're nearsighted. If I take a piece of paper and I look at that piece of paper, I can read it fine. I'm nearsighted. I can see nearby. I can't see far away. I can see the pieces of paper on the back wall. I know that each of those pieces of paper back there say period 1, period 2, period 3, period 4, but I can't read that. If I didn't know what it said because I saw it 5 minutes ago, I wouldn't know that it said period 1, period 2, period 3, period 4. My prescription is in the range of minus 4.25.
Wow.
Negative 5. Wow. Negative 4.5. That's relatively strong, although it's not, that's also fairly common to have that prescription. Most of you guys probably don't have a prescription that's quite that strong yet. Some of you will. Okay, my son, who's 11 years old, just got new glasses, minus 3.25. His prescription went by almost a full point over the last year, from minus 2 point something to minus 3.25. Okay, it happens. If you were farsighted, by the way, and you needed reading glasses, your prescription would be positive something. Basically, what we're saying here is that, look, I need a lens with a negative focal length in front of my eyes. I need a concave lens. Okay, it's got a negative focal point, a diverging lens. Versus if you're farsighted, you need something like a magnifying glass, something that's thicker in the middle, thinner at the edges. You need a positive focal length. So my glasses are minus 4.25. I've got what we call high index lenses. What does that do? It bends light more. Right? If I need to bend light quite a bit when it goes into my eye, more than most of you need. Kelly needs to bend it quite a bit as well. Hers are minus 5 or, what did you say? Minus 4.5, just a little bit worse than mine. She needs to bend light a lot as well. She's probably, when you wear glasses, probably have high index lenses as well. Otherwise, they're going to be pretty thick, right? The higher the index of refraction, the more it bends light. So you don't need as much thickness to accomplish the same thing. Does that make sense? How many of you guys had my wife as a teacher in grade 1 or grade 2? Grade 1 and 2. Wow. Just grade 2? My wife's prescription right now is about minus 11.
Oh my God.
She has like super high index lenses. We pay a fortune for her glasses. Her glasses aren't any thicker than mine. But the index of refraction of the material, I'm not sure what even material is used in those lenses. But whatever material it is, has a super high index of refraction, which bends light more bends light quicker than mine do. Okay, I don't need that high of an index because my glasses aren't going to be that thick with my prescription. But if you're minus 11, okay, you need super high index. Now, works well. Works well. She can see pretty good. The downside to that is that she's got, she can't see perfectly around the edges of her glasses. Because when you've got that high of an index and it's bending that quickly, it's difficult to get the prescription that perfect. She can't see great around the edges of her glasses. She can see, but not perfectly around the edges of her glasses. Looks straight on, she's good. Looks around the edges, not so good. The other thing is, and you notice this to some degree with everybody, okay? I look at everybody with glasses on right now. Okay, I look at everybody with glasses on right now. You never notice this unless you're actually looking for it. But then once you see it, it's like, can't miss it. If you look through my glasses right now, you probably see my eyes in like this. Do you see that? Like my face doesn't go straight down, it goes down. Like if here's my face, okay, and I put glasses in front of my eyes, really big glasses. Those are 1980s glasses. What you'll usually see here is this. Because not only does it refract the light going into my eyes, it refracts the light bouncing off of my face coming out of my glasses as well. The higher the index of refraction you have, the more you notice that. Okay? So my wife has an index of refraction of, I don't know what the index of refraction is, but her prescription is minus 11.25. If you look, I mean, you can see that, right? You can see that noticeably. You don't notice it unless you're actually looking, but you can definitely see it. When I look at you guys, okay, I can see it in all of you, but it's almost not perceptible because your prescription isn't nearly that high. Okay? You don't notice it so much until you look at a photo, like a picture, right? If you look at grad photos, your grad photos with your glasses on, you might notice it. Yep.
So your prescription, like, does it get higher the worse your eyes are?
Yes.
Is that how it works?
Yeah. I don't think you can get to minus 50. Yeah.
If you're farsighted then,
Yeah.
far away, would that mean like it would be really magnified, like your eyes look bigger?
Yes. Yes. Yeah, no. No, that's exactly it. If you are farsighted and you need reading glasses, when you look at yourself or look at somebody else with those reading glasses on, those eyes don't appear to come in like they did right there. Rather, they go a little bit further out, closer to the edges of the lens. Does that make sense? Bifocals are both. If you need bifocals, then you have concave lenses at the top, okay, which are diverging lenses. Notice that's the opposite of mirrors, right? Concave is converging for mirrors. It's diverging for lenses. But we'll deal with that in a lot more detail later on. Okay, you need concave or diverging lenses at the top, and at the bottom, you need the opposite. You need convex or converging. It used to be so that there was a distinct line, and now they have progressive bifocals, so they kind of do it so that that somebody looking at you doesn't notice that you have bifocals. But people that wear those still have to kind of look up to see far away and look down to the bottom of their lenses to see close up. You have glasses, I have glasses, you will need bifocals sometime in your life. So will I. You'll need bifocals. You'll need bifocals. All of you that wear glasses will need bifocals. All of you that don't wear glasses may never need glasses like I have, but you will also need reading glasses at some point in your life. Everybody will. The muscles in our eyes weaken. We can't change the shape of our lens to change the focal point of the lens in our eye to see things properly. Okay? You will need bifocals. Sorry, not bifocals, but reading glasses at some point in your life. If you live long enough, you're going to need reading glasses at some point in your life. All right. let's look at 4 practice questions that go along with that. Page 668, please. Let's do questions 1, 2, 3, and 4. Let's see what you can get done on those right now. We're not going to assign those as homework because you've got a few questions as homework on on mirrors already. You're also going to have a little quiz tomorrow. Quiz tomorrow is just going to be on curved mirrors. So there'll be one question. Basically, it'll probably be asking you to draw a ray diagram, and it'll probably ask you to calculate something with regards to that ray diagram that you've got. So ray diagram, and then a calculation for the same scenario, right? And then we'll give you a few minutes to work on these tomorrow if you don't quite finish them up today.
This period, you know that will not